right, let me just untangle a wire and then we'll get started. Does anyone know how to make this thing at the top of my screen disappear? Ah, there we go. Okay. All right. Great. So what I want to talk about today is a relationship between two different theories of how to count curves inside threefolds. And so in order to do that, I want to start with an overview of the 5 million ways to count curves in threefolds. And so this may be slightly boring for the experts, for which I apologize in advance. So we're going to start with a thing called TT theory. So this is Donaldson-Thomas. Morally speaking, there's two approaches to how to count curves, and one is where you view the curve as a you fix your favorite curve and you look at all maps from that curve into your threefold. And that's the approach of stable maps. That's not what this is. This is where you say I fix my threefold and I will look at all, in some sense, embedded curves inside that threefold. And so if we're going to count curves, we need some kind of moduli space of curves. And this moduli space here will just be some kind of Hilbert scheme on your threefold of curves. And here when I write curves, I just mean objects which are one-dimensional. One-dimensional ideal sheets in some sense. Okay. So to be very concrete, this means you're thinking about ideal sheaves of a curve C, and these fit into a shorting stack sequence. Actually, I just realized I'm more used to calling the threefold Y, so let's call it Y. And this ideal sheaf is a subsheaf of the structure sheaf of the threefold, and its quotient is the structure sheaf of the curve which you want to count. Okay, so this C here is the curve. Okay. Now, when we say we want to count curves, it's not enough to just have a moduli space. We want the information of the tangent space at each point of your moduli space. And because here our moduli is not very well behaved, we want a thing called the virtual tangent space. Okay. And this will be T ver. This is like a stand-in for the usual tangent sheaf, except it's much more better behaved. I don't want to go into the actual details here, but if you fix your ideal sheaf, I, then the virtual tangent space at that point in your moduli space will just be something like chi of the structure sheaf minus chi of the ideal with itself. Okay. And so once I tell you these two pieces of information, you can essentially go ahead and write down a whole generating function of curves in this particular curve counting theory. And your generating function will be some kind of function. Okay. So this will be some kind of generating function of curve invariance. And we're going to do this in K-theory. So instead of writing an integral over the space, we're going to write a K-theoretic integral, which will just be an Euler characteristic over the moduli space. And here we're going to put the virtual structure sheaf, possibly with some symmetrization. And I don't really want to go into detail about this, because in the end, we're going to focus on the case. So we're only going to work in the case where Y is toric. So this will be an assumption that we make. And there are some very general degeneration arguments where using which you can just assume that you're in this case. And the nice thing when you're toric is that then you have an action by a torus, and you can apply localization, as we hopefully all know. And you can localize all the way down to each torus chart. So instead of thinking about an arbitrary Y, we're going to think about essentially the single building block of the theory is a case where your threefold is just C3. Okay. And then you can ask, what are the fixed points? If we want to apply localization, we need to know explicitly what the fixed points are. And you can show that the fixed points, these will be, so what will these be? These are T-fixed ideal sheaves. And so if you have an ideal sheaf, well, okay, first of all, since we're working on an affine space, we might as well just think of this as a, so what is this ideal sheaf? On C3, this is just some CXYZ module, right? And for this module to be fixed under the action of the torus, it must be the only possible generators it can have will be some collection of monomials. And what's very nice about C3 and every other toric thing is that you can just literally draw what these monomials are. You can say, I'll look at the weight space. So this is X, Y, Z. And for every monomial inside this sheaf, so let's say you have a monomial xi, yj, ck. Okay. Then what you'll do is you'll draw a box at that exact coordinate. Okay. At I, j, and I'm not sure how to draw the next coordinate, but I'm sure you guys get the idea. And so how will these blocks be laid out? Well, the only criterion for which arrangements of boxes are valid and which are not is that this ideal sheaf has to form a module, right? So if I stick a box in some place inside this grid, then this box, well, if you take this particular monomial and you multiply by x, you're gonna get one more box over here. And if you keep multiplying by x, you see that all these boxes have to exist. If you keep multiplying by y, you see that all these boxes have to exist. And you keep multiplying by z, all these boxes have to exist. Now, since you don't really want to draw an infinite number of boxes, well, you don't want to draw too many boxes. You want to draw as simple of a diagram as possible. We're not going to draw the boxes for the actual ideal sheaf. So it's actually equivalent to just draw O of C instead of I of C, right? Because if you think back to the short exact sequence, the only piece of data we have is either what the ideal sheaf is or what the structure sheaf is, and you're free to draw either one. Either one will specify which point you're at inside the moduli. And so if you think about what the structure sheaf is, well, it's essentially all the boxes which are not in the ideal sheaf. So in general, O of C will look like some kind of 3D partition, possibly with infinite legs. So what do I mean by infinite legs? I just mean, well, let's think of the simplest possible case, right? What's like the simplest curve inside C3? I can take something like a curve which runs along the x-axis. This is the module C adjoint x. Right? This is the side C Z. Right. And so what does C adjoint x look like? It's just a whole chain of boxes along the x-axis. Right. So I'm very bad at drawing boxes. I'm sure there are many people in the audience here who are much better than I am. Essentially, you're going to get a whole infinite chain of boxes, and it keeps on going. Right. And of course, more generally, you can get all kinds of legs. Let's say you have some non-trivial thing over here. Okay, I'm very bad at drawing these. Please excuse my bad drawings. Okay. And you can get some stuff over here and some stuff over here. Okay. So in general, you're free to specify 3 types of asymptotic data. You're free to specify partition here, partition here, partition here. And you can say, I want to think about all fixed points with these 3 specified legs. Okay. And so in general, we can collect all this information together into some kind of like local partition function for C3, and this object is called the vertex. So this, oh geez. After 3 months, I still haven't figured out which hand gesture is causing that. Anyways, so the vertex is some huge function. You specify your 3 asymptotic partitions, lambda, mu, nu. And it will be a series over all 3D partitions pi with legs, lambda, mu, nu. And you want to record the size of your 3D partition in some extra variable. And then for each 3D partition, you'll have some weights. And this weight is not so important, so I don't really want to say too much about it, but this is where the information of the virtual tangent space goes in. what I've written down here is essentially some kind of localization formula for a k-theoretic integral over the moduli of the vertical distribution. Okay, that's a very brief review. And just so I'm not boring the experts too much, maybe here I'll say that I've written down a very short expression, but this is slightly misleading because in general this whole function will be very, very complicated. And in fact, you should not try to compute this by hand by any means. You should always try to do this via software. And so I want to show you guys what this roughly looks like in software. Okay. So here, so can everyone still see my screen?
Yep.
Is it okay? Okay, cool. So here you can see I have some code, and this code implements the vertex for this particular theory. And this vertex will be a series. And let's just truncate the series at like 3 terms in Q or something. And here, just for simplicity, I'm only taking one non-trivial leg. You see it's the non-trivial leg in the y direction, and that leg has profile 3, 1. Let's just run this, and you'll see a huge series pop up. This might actually take a bit of time, not because the computation takes a long time, but because the series is so huge that it takes a while to render. Anyways, you can see by the size of the scroll bar that this series is not that pleasant. Okay. So anyways, I do encourage you all, if you have some time, to play around with these vertices. They're
what are x, y, and z in the formula?
So these x, y, z, these are so we want to keep track of so we're working inside equivariant K-theory, which means we keep track of equivariance. And here we have a 3-dimensional torus acting on the whole theory, and x, y, and z are the weights of that torus. Okay, so
I see, thanks.
Essentially these coefficients, these will all come from this a hat term. It's kind of like in cohomology, if you do an equivariant integral, you'll get non-trivial functions of x, y, z as the coefficients. Okay. Okay, so I should hurry up. That was a brief review of DT theory. Okay. Now, there are some problems with DT theory that we want to resolve. One problem is that this moduli space is way too complicated. If you think about an arbitrary one-dimensional curve C, this C, oops, the C inside your threefold, sorry, not Y. It could be all kinds of things, right? This C may have 0-dimensional components. It may be some horrible curve. And in general, we want to work with a nicer moduli space. Now, one thing we're sure we want to get rid of is exactly these floating 0-dimensional components. You can imagine that you have your threefold, and you really do want to count actual curves in it, right? Actual one-dimensional things. You don't care about all these floating points around here, which may be part of your one-dimensional subscheme. So to remove 0-dimensional components, there's 2 ways you can go about this. One way is you can say, I'll try to do this completely algebraically. And I'll take my v lambda mu nu. Okay. And I'll just manually quotient by the contribution from purely zero-dimensional curves. And if you think about it, purely zero-dimensional curves are essentially the ones whose legs are empty. Where you take v empty, empty. And this will result in some theories in Q. Okay. But it would be nice if you had some like actual moduli space that produces this series immediately, as opposed to you doing this whole algebraic thing where you manually quotient out by. Yeah. And the miracle is that we do. This is the PT theory, which I think Yasha spoke about very briefly a few weeks ago. And very roughly speaking, what's PT theory? PT theory is where you say, okay, we used to have, so let me do a comparison with PT theory. We used to have a short exact sequence like this. Oh, sorry. Now in PT, we relax the condition that this map has to be surjective. Okay, so we say we have a map from OY to some sheaf F. This is a map S. And it might not be an actual surjection, but at least the cokernel, so this Q here, this is the cokernel S. We don't want this cokernel to be too big. Okay, so we'll impose the restriction that the support of Q, a Q really is like a zero-dimensional sheaf. And we're also imposing the condition that this sheaf F is pure, is a pure one-dimensional sheaf. So what does this mean? We used to count these structure sheaves, OC of curves. And these structure sheaves could have curves and random points just floating around everywhere. Now, if we count these sheaves F, these will still be one-dimensional curves, possibly with some zero-dimensional points embedded in it. And that's what this cokernel is trying to capture. So in some sense, we've constrained these free-floating points to lie just in your curve, as opposed to scattered around your ambient three-dimensional space. So you can write down a vertex for PT theory as well. I don't want to go into the actual technicalities of how to do that. And there's a DT-PT conjecture, which essentially says that the resulting vertex, VPT, and mu is exactly the same as VDT lambda mu nu with this normalization where you throw away all the zero-dimensional things manually. Okay. And this is not known in general. It's known in some particular limits. Now, before we move on, there's a slightly different way to phrase PT theory, which will be important for us slightly later, which is that the passage from PT to PT theory, you can think of it as some kind of wall crossing. Inside this huge space, okay, so there's some chamber called DT and some chamber called PT, and there's a wall. And the space is, in some sense, morally speaking, Bridgeland stability conditions. on the BCO of your threefold. To be more precise, there's this. So what does Bridgman stability entail? It entails the choice of a heart. It entails the choice of an abelian subcategory, which you call the category of.
Hi, Henry. I think you want the category of roughly one-dimensional sheaves. Otherwise, it's
Right. Yes, that's right. So strictly speaking, I should say one-dimensional sheaves. And so here, you can phrase PT theory in the following way. You can say, I'll write down a subcategory T. This is called the torsion subcategory. This is all sheaves, all one-dimensional sheaves on Y, which are actually zero-dimensional. Sorry. Okay. And there's a procedure by which you can tilt the heart of your category with respect to this subcategory that you've picked. And what is the tilt? It's the subcategory of pairs, which essentially is this, where you say something like this first sheaf F is inside the subcategory F, second sheaf Q is in the subcategory T. And so PT theory can be viewed as a tilt of the standard heart with respect to this particular torsion pair. Okay. So, right, I should say, these pairs, FQ, these are called stable pairs. Okay. Well, that explains half of my title. So now I should explain the other half of the title, which is the Quasi Map. So Quasi Maps are a slightly different way to count curves. Okay. So roughly speaking, if you have a GIT quotient X, say G. Sorry, that's not what I want. That's not a GIT quotient. We'll reserve this notation for stack key quotients. Let's say you have a GIT quotient M mod G. Okay. And so what's a quasi map? It's roughly where you say I fix my source curve C and I want to map it into X. And you say this is roughly the same as a map from a curve C into the stack M mod G. And this is actually the same as a principal G bundle P on your curve. And the and a choice of section inside something like P times M. So very roughly speaking, you have your curve C, and on top of it, you have an M bundle. And for each point in C, you just pick some kind of G orbit inside M. Okay. Now, this is not exactly what a quasi map is, because we don't actually want to map to this entire stack. Inside this entire stack is X. X is open inside the stack. And so a quasi map is this package plus the condition that f of a point on your curve is actually inside X for all finitely many points on your curve. Okay, so this is some compactification of the locus of actual maps from your curve C into your space X. Okay. Now, for various reasons, it's very productive to study quasi maps when X is a Nakajima quiver variety. I don't really want to go into the details of what Nakajima quiver varieties are. Most of you were in Andre's course. So let me just say the two standard examples. The two simplest examples here are cotangent bundle of leg varieties, over schemes of points on C2. Okay. And it's great that the Hilbert scheme is an example of a Nakajima quiver variety, because now we can try to do a comparison between quasi maps and some kind of sheaf counting theory on the threefold. Right? So we'd like to ask how quasi maps can possibly be related to DT or PT theory. And roughly speaking, the answer is, if you think about a quasi map from a curve C to Hilbert C2, so what really is this? If you try to graph this, right? So here's your curve C. Maybe here's the C2. Here's your curve C. Then you'll essentially end up with some kind of subscheme inside C times C2. And roughly speaking, it might look something like this. Sorry, it's not exactly accurate, but let me leave it like that. So the graph is some kind of subscheme in C times C2. And you can start asking if, well, anytime you have a one-dimensional subscheme in a threefold, you can start asking like, which moduli of sheaves ought it to live inside. And so this is not exactly DT theory. So this is not the same as taking DT theory on C times C2. And the reason is because inside DT theory, you have these zero-dimensional things floating around, components. And well, I guess in this particular case of the Hilbert scheme of C2, this really actually is the same as PT theory on C times C2. And we'll see this later as a special case of what I'm about to explain. So we'll see later. It should not be too surprising. I mean, well, okay. That's what I want to say next. So actually, here maybe I should add one more example, which is that not only can you get the Hilbert scheme of C2, you can actually get the Hilbert scheme of any ADE surface. Hilbert scheme of this. Okay. And so let me say briefly what's an ADE surface, right? And ADE surface S. This is a resolution. This is a resolution of the ADE surface singularity of the form C2 mod gamma. And gamma will be the corresponding ADE subgroup of SU2. Well, let's say SL2C. Okay. These are finite subgroups. And for the sake of exposition, we'll think only in the case of type A. So for type A, S is a resolution of C2 mod gamma, where gamma is equal to Z1n. And we'll call this curly A sub M minus 1. Okay. And so this AM minus 1 is toric. It's a blow up of some singularity on C2, and its toric skeleton looks something like this. So what do we have? We'll have what used to be the X and Y axes. On C2, and then we'll have a chain of exceptional divisors, something like this. And how many exceptional divisors will there be? There will be M minus 1 exceptional divisors. And each of these will be a P1. P1. Sorry. Okay. So we can try to repeat the same story, except with quasi maps to Hilb of a ADE surface. You can think about quasi maps to Hilb on ADE surface S. And you can ask, is this equal to PT theory on your curve C times S? Which is what your naive first guess would be if you were working off the Hilb of C2 case. And the answer here is no. This is not the same. And there's a very straightforward reason why this is not the same. It's because now if we think back to the whole graph business. So now I have to draw something more complicated. It looks something like this. Right. So now what's a quasi map? A quasi map will still be some curve which looks like this in some sense. Okay. But now, what does PT theory look like? PT theory is allowed to have curves which are purely supported on compact exceptional divisors like this. Right. It's not the case that every that every one-dimensional subscheme inside C times S inside PT theory must have must have non-trivial class along the curve C. Right. So PT theory has these unwanted curves lying purely on exceptional divisors. Which we'll call E. And so then the very natural question is, if we somehow remove these extra contributions, is the resulting theory, whatever that's called, equal to quasi maps to Hilbert S? And so now we find ourselves in a situation which is very similar to the passage from dt to pt, right? To move from dt to pt, we said, okay, we have these free-floating zero-dimensional points. We want to remove them. Now we have these one-dimensional curves along the exceptional divisor, and we want to remove those as well. So there's two ways you can do this. You can say, I'll take the vertex for PT, and I'll just manually, algebraically remove the part which comes from PT curves which lie purely on the exceptional divisor. This is I don't know, PT on the exceptional divisor, on exceptional divisor. So that's one way to go about it. The slightly better way is to find some kind of actual geometric theory which producing this. And this has been done. This has been done by Bryan and Steinberg. And the idea is is basically analogous to how you can tilt DT theory to produce PT theory. So we'll say, we'll define the subcategory T to be all sheaves Q, all one-dimensional sheaves. Okay. And here there's a slight subtlety. You don't just want all the curves which are supported on the exceptional divisor. You actually want the ones which are supported there but behave cohomologically like points. So you don't actually want H1. You want their H1 back. I should say this pi here. This is the resolution. This is the resolution from your ADE surface to the underlying singular space. So we can tilt with respect to this.
And R1 is zero-dimensional.
R1 is just zero. It's not even zero-dimensional. It's
R0 is zero-dimensional.
Sure. Yes. R0 is zero-dimensional. Thank you. C2. Okay, great. Okay, so now we should think we're trying to count pairs where you have the sheaf F. Sheaf F has a map from the structure sheaf over threefold. And then there's a co-kernel Q. And Q is inside this category T. So this is almost exactly like PT theory, except we're allowing the co-kernel to have more stuff. And you should think of the more stuff as just extra things which are supported on the exceptional divisor. They may be one-dimensional, but cohomologically, they behave as if they were zero-dimensional things.
Is this map, so R0, is it a sheaf on this quotient or the quotient times the curve?
Oh, I'm sorry. Yes, you're absolutely right. Thank you, Noah. Right, so maybe instead of saying that pi is the resolution of the surface, I should say something like pi is the resolution of the threefold. Something like this. All right, thank you. Okay. And so, as in DT or PT theory, you can write down a vertex for this new theory, V. But now this vertex is slightly different from the DT or PT vertices. So in the usual DT or PT pictures, your fundamental building block is C3, right? This is like the only affine chart of any toric threefold. Here, this theory by B and S, which we'll abbreviate as BS theory, this will depend on the choice of a resolution pi. And you can't really break up things like an AD surface any further, right? You can't just somehow break up the resolution. So the fundamental building block of this theory, at least for the threefolds we want to think about, will be things like ADE surfaces. Okay, so vertices, so the vertex will be some kind of integral, well, some kind of object on the ADE surface. Okay. And so very roughly speaking, what will it look like? You'll have your ADE surface. You'll have your curve. So here's your threefold. This is your threefold line. And as usual, you'll be able to specify some kind of asymptotic legs along each of these red curves. So you specify your favorite partitions here. Sorry, I'm really bad at drawing these for some reason. You'd think I'd be better. Something like this. You specify your legs. Oh God. I apologize for my horrible drawing. Okay. Then some kind of mystery happens here. Okay. And if we have time later, we'll get into this.
Yeah, is there a mental picture suggestive of which Q are allowed? We think of these as sheaves that don't build up in the Y direction or something.
So I'll talk about this in more detail later, but for now, what you should think is this will essentially, in terms of drawing configurations of various boxes, this will look kind of like a DT configuration where you're allowed to have extra boxes here. Okay, but they're constrained to behave in a very specific way, which I'll talk about later.
Okay.
Yeah. Okay. So in particular, these configurations of all these boxes may have non-trivial degree along the exceptional divisors. So may have non-zero degree, may have non-zero degree along. Okay.
And is there some kind of heuristic reason why these conditions, these conditions on Q are the right things to think about?
Right things to think about. Well,
not right is maybe the wrong word. But.
Yeah, I'm not sure if I have a good answer to that question, other than the heuristic which I essentially just said, where you say I acknowledge that that I want to throw away one-dimensional things on the exceptional divisor, but it turns out if you just throw out all of them, that's just way too much. And beyond that, I don't know, you can run some computations and you can see that there's a PT-BS correspondence. So maybe this is like a weak or strong evidence, depending on your perspective, that you have the right theory, which is that if you write down your vertex inside this new BS theory, I'm sorry, I should say, so here I've written down what's called the one-leg vertex. Here I've roughly drawn the one-leg vertex. And when I say one leg, I just mean that essentially out of the three distinct asymptotic directions, here, here, and here, I've only put infinite legs on one of them. Okay. Of course, in terms of actual boxes, there's more than one leg, but they're all pointing in the same direction. In principle, you can try to write down a two-leg or a three-leg BS vertex. The combinatorics of how to plop down boxes inside this picture probably will be more complicated. But for the purposes of comparison with quasi maps, well, there's not really a concept of two or three leg vertex in quasi map theory. If we think back to how we constructed quasi maps, right? Essentially the how to put it, there can't be contributions along these non-compact directions. It's only one leg along C. Okay. So you can try to do some calculations, and this one leg vertex will be indexed by an M tuple of partitions. This M tuple will specify the profile along the first leg, second leg. Sorry, I guess I should index starting from 0. That's my convention. Up to the M-1th leg. And you'll see that this really is equal to the PT vertex on the exact same diagram, modulo PT of the exceptional. Well, maybe here I can just write empty. Okay. And this is still a conjecture in full generality. But I think it's safe to say that in the literature, it's known in the same settings as where the DT-PT correspondence is known. Okay, so what would we like to say? We'd like to say something like we'd like to show that the quasi map vertex, the quasi maps to hilb of my ADE surface S is actually equal to this BS vertex. Maybe here I'll just like this. Okay. And in fact, we can show something stronger. So not only are these two vertices the same, actually these two theories are just completely equivalent. So more strongly, we have the following theorem. So this is the main theorem. That actually these moduli spaces are just equivalent. Now here I have to be a bit more specific about which moduli spaces are equivalent. Here I should say something like Quasi Maps to hilb S. Except here when we're thinking about the vertex, we're not really thinking about the entire quasi map moduli space. We're not thinking about the entire BS moduli space. We're thinking about the ones where Okay, maybe let me write this, and then I'll explain. This is things which are non-singular at infinity. And here we also want things which are non-singular at infinity, except on C times S. Okay. So here, what do I mean by non-singular at infinity? I just mean that, strictly speaking, these theories are all constructed over something like, so these are theories over something like, oh, okay, so let's put this. If you think about C being P1, has 2 points, 0 and infinity. Right. Say C is P1. Then when we talk about the vertex, we're thinking about things where you can have some non-trivial behavior here, then you have your infinite legs, and then there's nothing special happening at infinity. Right? Here, essentially nothing happens. Right? If you had your infinite legs, they would just keep on going until they hit infinity, and that's it. And you don't have extra components like along, say, the exceptional fibers at infinity. So roughly speaking, this non-singular at infinity means nothing happens at infinity. And the exact same thing here. These are the actual moduli spaces that we integrate over in order to write down the vertices. And so actually these moduli spaces are isomorphic. There's some kind of isomorphism, P tilde. And if you want the vertices to be equal, not only do you want an isomorphism of moduli spaces, so remember at the very beginning we said to write down the vertex, there are two ingredients. You need a moduli space and you need some kind of tangent obstruction theory. So associated to each of these theories, there's a T-ver. A T-ver for, let me write this here. There's a T-ver. Actually, let me do this in green because the rest was in green. There's a T-ver for Quasi Maps. There's a T-ver for DS theory. And these are also matched under the equivalence phi tilde. Inside K theory. So maybe it's the case that they really do match up as elements inside DB-Co, but I've only done the computation in K theory. In fact, inside equivariant K theory. Right. Equivariant K theory of okay. Now, of course, it follows from this that the vertices also match.
Kenny, I think you want to say they match in K theory the moduli spaces. No?
Oh, I'm sorry. Yes, you're right. Yeah. Inside, how did I write it? This whole thing is living inside the PS moduli. Oh, C. Thank you. Okay. So I think what's more interesting than and maybe diving headfirst into the proof of this is to see some applications of this. So how to put it? So So one thing a comparison theorem like this lets you do is now things that you used to only be able to say for quasi maps, you can now push them through this equivalence and see what they say about your sheaf counting theories on threefolds. So one very spectacular thing that you can use quasi maps for is this thing called 3D mirror symmetry. And so very roughly speaking, what's 3D mirror symmetry? So let me say it like this. It says that so let's go back to thinking about Nakajima quiver varieties. To build a Nakajima quiver variety, you start off with a quiver, Q. And what 3D mirror symmetry predicts is that there is a mirror quiver Q check. So this is a 3D mirror. And what do you do with this? Well, if you start with a quiver and you want to construct a Nakajima quiver variety, you have to pick some kind of stability condition, theta. This is a GID stability condition. And if you have these two ingredients, you can produce a moduli space, which is the Nakajima quiver variety associated to Q with the stability condition theta. And you can do the exact same thing on the other side. Oops, check. And here you'll get a mirror Nakajima quiver variety theta check, Q check. Okay. And 3D mirror symmetry predicts that these two quiver varieties have very intricately related geometries in both the classical and the quantum sense. Okay. So in particular, there is some way to match their quasi map vertices. So one thing you can use quasi map theory for is to probe this 3D mirror symmetry stuff. So how to write this? Maybe first I should say this is due to Mina and Andre. And the statement is essentially something like, well, there's many statements, but the one that's relevant for us is that if you try to write down the quasi map vertex for the Nakajima quiver variety on one side, there's a relationship between it and the Nakajima quiver variety on the mirror side. And what's the relationship? The relationship will depend on one extra piece of data, which is that you, how to say this? So on these Nakajima quiver varieties, there is an action by a torus, and you can pick a certain chamber for that torus, and this chamber is a choice of which directions you call attracting for that torus, and which other directions you call repelling. And there's a choice of dual chamber C check. And what 3D mirror symmetry will do, well, part of what it will do is it will swap theta with C check and C with theta. And this is actually part of a larger swap, because where does C live? C lives inside, say, the Lie algebra of that torus. And so actually the entire Lie algebra has to be identified with the space of GIT stability conditions on this side, which essentially will be something like pick. So actually these two things are slots. So when you want to write down the relationship in between these quasi-map vertices, you expect that they also will depend on your choice of attracting chamber. And so here you have to put this operator called the elliptic stable envelope. We will not go into the details of what this is. And this will depend on your choice of attracting chamber on the mirror side, which is the choice of the GIT stability on the original side. So usually you would write something like C check as a subscript, but maybe I'll abuse notation a bit and write theta down here. Okay. And there's all kinds of normalizations which have to happen in order to make this true. There's all kinds of overall monomial factors you have to multiply this by. I really cannot deal with those off the top of my head, so we're just going to write a tilde on top of everything to indicate that the appropriate normalizations must be done. Appropriate normalization. Okay, so let's try to push this through through this sheaf counting / quasi maps equivalence. So well, I guess once you push it through, there's a whole variety of things you can say. So maybe let me spoil it a little. One type of statement you can get after you push this through is you'll see that you very naturally get an application to this thing called the DT crepant resolution conjecture. So what is this? This essentially works as follows. It says if you start with a threefold Y, which is a resolution of a sufficiently nice orbifold, which we'll also call Y, except it'll be curly. Okay, so this is an orbifold. This is a resolution. Okay. Sorry, crepant resolution. It's very important here that it's a crepant resolution. Then, in general, there's this whole philosophy of various kinds of crepant resolution conjectures, which say that there is some kind of relationship between the quantum geometry of the thing upstairs and the thing downstairs. The specific statement that we care about is a sheaf counting version of this, where you say something like, if you write down the vertex for PT theory of the orbifold Y. Okay, so there's some notion of an orbifold PT vertex, which we'll call the orb. Versus if you write down upstairs the Bryan and Steinberg vertex of the thing upstairs. Now these two things ought to be equal. And here I'm writing equals like this because we have to be a little bit careful. These two objects are a priori series in some variables, but it turns out that this equality is how to say this. Maybe here, let me just write re-expansion. In the literature, you'll often see people say that these are equal as rational functions. Let me not say too much more than that. Okay, so let's assume we knew nothing about the crepant resolution conjecture. And let's just try to push this whole thing through to the quasi map side. So we can start off with the PS vertex for my threefold Y. And we can apply this correspondence, this PS quasi maps correspondence. And we'll get the quasi map vertex. And again, for simplicity, we're going to say that Y is just, say, AM minus 1 times P1. Okay. And so here we'll get the quasi map vertex for Hill AM minus 1. Similarly, if you take the orbital PT vertex, actually, maybe here it's somewhat important to say this orb up here is not so special, not in this case at least, because what's the orbifold? The orbifold will be something like C2 mod gamma. Well, it is C2 mod gamma times P1. And the orbital PT vertex here is essentially the usual PT vertex for C3. So this is essentially just the usual PT vertex, except you keep track of the gamma equivariance. So the way people like to say this is that you have colored boxes. You have m different colors, and you have some new variables which record the total number of boxes of each of the m colors. Now, maybe here, I forgot to say something earlier. Some of you may have observed this already, which is that if we come back and look at this PS quasi maps equivalence, I wrote this down for ADE surfaces, but if you just think about the case of a type A surface, right? A type A surface with no exceptional divisors is the same as C2. So actually, so here let me write in brackets. If you try to do BS theory on the trivial resolution, just C2 resolving itself. Sorry, maybe I shouldn't write it like this. C2 times P1. This is exactly the same as PT theory, literally by definition. Okay. So as a consequence, you recover the special case of quasi maps of Hilbert C2 corresponding to PT theory on C3. And so why am I saying this? It's because now you can say also via the PS quasi maps correspondence. Here we're going to get the quasi map vertex for Hilb, not of C2, but of C2 mod gamma. So again, this is almost exactly the same as the usual quasi map vertex for Hilbert C2, except everything has to be gamma equivariant, and you keep track of gamma equivariance. Now, on the quasi map side, there's a lot to say about the relationship between these two vertices, because it turns out that these two spaces, this Hilb of an ADE surface and Hilb of the underlying orbifold, these are both Nakajima quiver varieties. And not only are they both Nakajima quiver varieties, they're both quiver varieties for the same quiver with two different choices of GIT stability. So two things are both MQ. Sorry, maybe first I'll say the quiver is your usual affine type A quiver. Whole bunch of nodes, they're all in a cycle. And you have one framing vertex here. And these two things will be M or Q for two different stability chambers, which we'll call theta plus and theta minus. For those of you who have thought about this in the past, the whole wall and chamber structure essentially looks like a whole bunch of lines passing through the origin like this. And theta plus will be somewhere over here, theta minus will be over here. Not super important exactly where they are. So now we think back to 3D mirror symmetry, and we ask what is 3D mirror to these two Nakajima quiver varieties, and the answer is that Q is well, okay, maybe let me not say too much about the quiver. The space which is mirrored to both of these is the moduli of rank M instantons on C2. And so this is exactly like the Hilbert scheme on C2, except instead of a rank 1 ideal sheaf, you think about rank M sheaves. Okay. And so then you expect a relationship between the two quasi map vertices on the original side with this mirror, and they're both related to the same vertex, except, sorry, up here, the relationship will be by the elliptic stable envelope associated to theta minus. And this will be the elliptic stable envelope associated to theta plus with appropriate normalization. Okay. So what does this say? It says you should expect a relationship of the following form. You should see that the orbifold PT vertex of the underlying orbifold will be something like stab theta plus inverse, stab theta minus inverse, apply to the, sorry, I did this backward, didn't I? Let me change this. This is PS of Y. This is PT or the order. Now, usually when you see the crepant resolution conjecture in the literature, people are not working in equivariant K theory yet. So in fact, there's some particular limit you can take, which is called the Calabi-Yau limit. Okay. And what this will do for you is essentially it will remove all traces of equivariance. Okay, so it's some specialization where the variables x, y, z just vanish. And in this particular limit, sorry, I forgot to hold up here. In this particular limit, this whole operator will become very trivial. It's essentially completely diagonal. It's just multiplication by some monomial. And you recover something like in the Calabi-Yau limit that these are equal, maybe up to some prefactor. And to the best of my knowledge, I think this is known. But I don't know if this has been written down anywhere. Okay. So maybe, actually, maybe I should say that from this perspective, it's actually very easy to give a proof of this statement. Completely, well, not completely independently, but it's very easy to see how this arises. Essentially, this arises because in the Calabi-Yau limit, right? So what are we actually trying to compare? We're trying to compare the Quasi Maps of some Nakajima quiver variety in one chamber with the Quasi Map vertex of a Nakajima quiver variety in some other chamber. And taking the Calabi-Yau limit on the original side is the same as just removing all the Kähler variables on the mirror side, because those two sets of variables are interchanged. And so in the Calabi-Yau limit, these two things essentially become sim of the tangent spaces, of half of the tangent spaces, maybe with respect to like, maybe with respect to C check plus of moduli sometimes. It's a sim with respect to a slightly different chamber, C minus of the moduli sometimes. And it's really not difficult to compare these two, because essentially what's happening, you have some tangent space, and you're asking, how does the attracting part of this tangent space change as I change what I mean by attracting? And if you remember that every Nakajima quiver variety is actually symplectic, what does that mean? Imagine you had a weight small w in here, right? Then if you've changed your attracting chamber and small w is not in here, well, then its symplectically dual direction must be in here, right? This is H inverse, W inverse. Here, maybe to be careful, I should write H bar check, right? So roughly speaking, if the left-hand side looks like a product over weights of something like 1/1 minus the weight, the right-hand side will look like something product of weights of something like this, where maybe only some subset of weights gets flipped, but that's essentially the idea. In the Calabi-Yau limit, this h bar check. So C1 limit means this h bar check is being set to 1. And so then you're basically trying to compare two rational functions, which are the same up to some overall monomial factor. And that overall monomial factor, well, that's that prefactor here. Okay. So maybe in my last remaining 3 minutes or so, I want to briefly say how one goes about proving this correspondence between the BS and Quasi Map theories. Proof of this. And I think the idea is conceptually very simple, but the execution was slightly annoying. So how does this go? So let's think about what this whole BS moduli space really parameterizes. It parameterizes, so it will parameterize certain sheaves F, which are one-dimensional sheaves on a space like AM minus 1 times C, let's say. Okay. And what does Quasi Maps parameterize? Well, I didn't go into any detail about this, but essentially, a usual Nakajima quiver variety you can think of as parameterizing quiver representations of your quiver. And if you want to upgrade that to Quasi Maps, you're essentially upgrading from vector spaces to coherent sheaves over P1. Okay, so now you think of a Quasi Map as still a representation of your quiver, but now it's a representation into the category of coherent sheaves on P1, certain coherent sheaves. So your Quasi Map will be some collection of coherent sheaves on P1, which I'll just write as one giant bundle. This will be coherent sheaves on let me just write C here as well, because here we're thinking about the vertex. And for the vertex, nothing special happens at infinity. Okay, so this is like the C, which is everything but infinity on P1. Okay. Equivalently, this is the same category as coherent sheaves on C2 and C. Right. There's an equivalence of categories here, where you just send your sheaf to a skyscraper at the origin. This is the inclusion of 0 into C2. Okay. And so now you look at this. Oh, actually, maybe to be completely correct, there's some gamma equivariance here. And this essentially arises because this is not some random collection of sheaves over P1. Yeah. Anyways, so now we look at this category, and we look at this category, and we realize that these categories are actually related via the derived McKay equivalence. Which says basically that. It says if you take coherent sheaves, or if you take dB co on AM minus 1, this is the same as taking dB co gamma equivariantly on C2. So there's some kind of equivalence of categories phi here. So in our setting, we just have to lift this up. We have to do this thing relatively over C. But it would be nice if it were that simple. There's some technicalities because this whole BS moduli space, it's not this entire category, and similarly the quasi map moduli space is not this entire category. You really have to make sure that certain subcategories of the stable objects actually match, and that's the annoying part I was talking about. But actually, using this derived McKay equivalence, right, pretty straightforward to see that fixed points are in bijection. That's essentially a short computation. Once you've obtained an explicit description of fixed points. And it's also a short computation to see that the virtual tangent sheaves match. And really the annoying part is to match the stability conditions. Okay, so I think I should stop now. I think I'm a few minutes over time, sorry about that. Any questions?
Yeah, I'm sorry, maybe you mentioned this before. So for the PT-BS correspondence, is there a map from one moduli space to the other?
Yes, there is. So actually this, everything I said past this point on the screen right now is actually very simple in the case of Hilbert C2, where you don't even need to run this whole derived McKay business, because I mean these how to put it?
Yeah, for Hilbert C2, everything is sort of, there's a, you can identify them, right?
Right. In fact, the equivalence here really is like I don't know, the identity map or something.
Yeah.
Sorry, not that equivalence. This equivalence.
Yeah.
Is essentially the identity map for quasi maps versus PT theory.
Yeah, for other cases, when PT is different from BS, there is a map you're saying from PT
right.
to BS.
Oh, from PT to BS. I'm sorry.
No. I mean, of course, the spaces are the same, but I meant for the PT theory.
Ooh, I would love for there to be such a map because because that would make proving some kind of PT-BS correspondence much easier. But I'm unaware of the existence of any such map.
Okay.
Yeah. It's like asking for a map from DT to PT.
Yeah, but yeah, I was just hoping that it exists in this case. There's maybe you can see at least vaguely. There's no issue with like degree matching for BS versus quasi map spaces. Is it like
no issue? Everything works exactly as you expect.
Okay.
Yeah. Actually, on the note of things like DT-PT or PT-BS, I'm not so convinced the best way to go is to try to exhibit some kind of map or correspondence. I don't know. I think lately I've been converted to the perspective that you should really try to control these kinds of objects, these DT, PT, or even BS vertices, not in terms of, not necessarily in terms of correspondences between moduli, but maybe in terms of representation theory. I mean, lurking behind all of these objects is this group UQGL1 hat. And
yeah, I was going to ask, can you see can you see this group on the BS side?
Yeah, that's a good question. I haven't thought about that. Yeah, I'm not sure if I can give a super meaningful answer, but ideally, so this is really just a dream, and it may totally be wrong. But ideally this UQGL1 hat should I mean it should show up in almost every chamber, not just DT or PT or BS, but every other conceivable chamber that you can pick. but I don't know. I haven't thought about this.
What about relative invariance?
I mean, if the entire moduli spaces are isomorphic anyway, I'm not sure if there's any merit to explicitly looking at the case of relative invariance.
I mean, I don't really know for BS our relative invariance like easily defined? Is it just straightforward?
Oh, I see. I don't see any issue in writing down relative invariance in the usual way. Yeah, I really don't.
Okay, then things probably.
It's really not that different from PT theory, except you have to be like the fixed points are a bit more complicated, but essentially, other than that, I think the structural properties of the theory should be the same as for PT. Actually, it's kind of a fun exercise to try to write down the BS fixed points. It will be in the paper, which will go on archive sometimes. Any other questions?
Yes. This from this, like the DT vertex is determined by evaluating it on threefolds of the form, like some resolution times curve where you only need to take quotients up to this cyclic group of order 3 or something. Like two surfaces are enough to pin down the vertex. Is that the same?
Sure.
Is that the same for this BS vertex, or do you really need to check all?
Oh, that's a good point. Well, I mean, speaking completely algebraically, if you believe this whole series of wall crossings from DT to PT to BS, it's certainly true the BS vertex is completely determined starting from the A2 case. Geometrically, actually, that's a good point. I'm not sure how to see this geometrically, because the fixed points for BS theory are actually kind of complicated. They like it's not good to try to split up the AM surface into like smaller AMs all glued together. I'm not sure if there's a nice gluing that will work there. Yeah, I'm not sure.
All right. Are there any more questions? If not, I'd like to encourage everybody to read the forthcoming paper because it's, well, I think has a lot of useful examples to learn from, and also to play with the code that Henry a little bit like the glimpse of that code Henry demonstrated. I think I was
right. Maybe here I should put in an advertisement, which is that the code is available on my website, and the 3-leg DT and PT vertices are on there. There's also an implementation of UQGL1 hat. Yeah, I hope it's user friendly.
Are there some high guidelines how people can contribute to that, or it's just?
So right now the code is on GitHub. I think if you want to contribute, you can. I'm kind of ashamed to say this, but I'm not sure how the standard contribution process on GitHub works. I'm sure you guys are all. I'm sure some of you know more.
Anyway, something to in the future. Hopefully, people will contribute, and also in the future, I think it'd be good for people to show some proficiency with this code as part of like oral exam or things like this. So it's I think it's great that there is now a code that computes all these basic things, which is somehow stable and maintained. So all right, let's thank Henry again for a talk, and we'll meet again in 1 week.
Thank you.